So once we have volume of water, our density of water, 1,000 times volume of water displaced times gravity, we can find VW. So 0.98 divided by 10 to the power 4. And this is giving us 9.8 times 10 to the power negative 5. As a volume of water displaced. And this is also equal to the crown is fully submerged. And so this value is equal to volume of crown. V of crown is therefore equal to 9.8 times 10 to the power negative 5 meter cube, because it is fully submerged in water. I hope this part is okay. Then
Yes.
we determine since we are looking for the density of the crown. Since we are looking for the density of the crown, we find the mass. But once we have the weight in air, which is 7.84 Newton, we can quickly do that without calculating for the mass before, because weight is equal to mass times gravity. This is also equal to density. Mass is density times volume. So we can find density of the crown direct from weight relation. We don't need to find a mass before we use density is equal to mass over volume thing. We can pick it directly from here. Therefore, the density of crown from this relation will be equal to W over VG. Okay. Then we substitute our value. Weight in air, 7.84 over the volume is 9 times 10 to the power negative 5 times gravity 10. So calculate that for
So
me.
please 9.8.
Sorry, 9.8. So calculate that for me. So you are 7.84 divided by 0.
Please, 8,000.
8,000.
Is that 8? Good. 8,000. 8,000 kilogram per cubic meter. Yes, I saw that some of you used gravity to be 9.8. Yes, 9.8. So it changed the value a little bit. Okay. So if the density of the crown is 8,000, meanwhile, the density of pure gold is 19,300. Compare gold, 19,300 kilogram per cubic meter. Then density of crown, 8,000. you compare, it doesn't come close to, not even half of this. The density of the crown is not even half of the density of gold. So it means the goldsmith took part of the gold, alloyed it, and then created the crown with. And so Archimedes should tell the king that the goldsmith stole part of the gold given to him. Now, this was a real story where Archimedes was taxed as such. And so, after going through his calculations, that was when he came out with the famous name Eureka. Because when Archimedes was given that task, it was a huge burden for him. He didn't know how to go about it. And so when one day he was able to, find a way out, he was so happy to the extent that they say, because I wasn't there, he ran naked, okay, in the streets of Greece and then shouting, Eureka, Eureka. Is that okay? And when the goldsmith was called upon and then was told the bare truth, in fact, he actually acknowledged the fact that part of the gold was truly stolen. It wasn't exactly the quantity of gold given to him. So by making that comparison, you could deduce the fact that, yes, he had stolen part of it. Please, I hope that's okay. If you have any question, quickly ask. Then we move on to it. A hot air balloon. Are you okay? All right. Now the hot air balloon. The hot air balloon, the hydrometer, all works on the principle of flotation. And the principle of flotation is that bodies float, okay? Bodies float when they have displaced volume of water equal to their own volume, that is the parts submerged, or bodies float when they have also displaced weight or mass of fluid equal to their weight or mass. That's basically the principle of flotation. So a hydrometer, which is an instrument used to determine the relative density of liquids or density of liquid generally, floats. The hydrometer is just like a pen. When you submerge the hydrometer in some volume of water, with a pointed edge, with a uniform, it has a uniform cross-sectional area. Uniform cross-sectional area with some graduation marks around it. Okay, this must be liquid. The more it sinks, the less dense the liquid is. So it's the hydrometer is something like this. The deeper it sinks, the less dense the liquid is. Okay. Now it works on the principle of flotation, which is mass of hydrometer equals mass of liquid displaced. Now, mass of hydrometer is also density. Usually, this can be given. Density can be density of hydrometer times the volume of hydrometer, which you equate it to density of liquid times volume of liquid displaced. Now, because the hydrometer is such that its mass can be determined easily by putting it on a scale or on a weighing balance, we can always know this component, mass of hydrometer. The volume of liquid displaced, volume of liquid displaced can further be broken down to volume is area times height. And here, this area, we are referring to the uniform cross-sectional area of the hydrometer. We are referring to the uniform cross-sectional area of the hydrometer. A. Then the height is the height of submersion, the level H. Okay, hydrometer is just like the marker or the pen with cylindrical cross-sectional area. Okay, it has a uniform cross-sectional area. So it's just like the pen. So the area can further be expressed as the area of a circle, pi r squared times h, meaning mass of hydrometer is equal to density of liquid times pi r squared times h. So this is actually the volume submerged. And don't forget the volume submerged, which is this. Volume of hydrometer or volume of water displaced, volume of water displaced, which is also the volume of that part of the hydrometer submerged. This is equal to volume of hydro submerged. So if you understand these concepts of how the volume can be expressed, how the volume can be broken down into area times height, this is only the area where we ask questions. Calculate the height, the depth of submersion, H. Calculate the cross-sectional area of the hydrometer. Calculate the radius of the hydrometer. If you understand this, that is the nature of the questions we usually set under hydrometer flotation. Okay, so quickly, let me go over for the last time. Pay attention. The hydrometer floats, so it works on the principle of flotation. The principle of flotation is that the mass of the hydrometer must be equal to the mass of liquid displaced. Okay, because the hydrometer is just like a pen, we can always place it on a weighing balance or on a electronic balance to find its mass. We can always determine its mass. So mass of hydrometer often known. So we equate, hey, my marker isn't. We equate the mass of hydro to the mass of liquid displaced. You can always express it in weight. But the point is that when you do that in weight, the gravity cancels out. The reason for which we are only concentrating on mass. So the mass of liquid displaced can also be density of liquid times volume of liquid displaced. Now the volume, when an object is submerged in liquid, the volume of liquid displaced is always equal to the volume of that part of the object submerged in the liquid. So when we manage to find the volume of that part of the object submerged in the liquid, we found the volume of liquid displaced. Okay. So assuming we don't know this, assuming we don't know the volume of liquid displaced, we can connect it to volume of hydro submerged. Volume of hydrometer submerged can equally be expressed as the uniform cross-sectional area, because I said it's just like a pen, or yes, the marker. The hydrometer is just like this. So its cross-sectional area is uniform from top to down. So area, cross-sectional area of the hydrometer times the height of submersion. I said the higher the submersion of the hydro, the less dense the liquid is. So if it submerges more, okay, then that length or height of submersion is what is represented as H from the surface of the liquid. So H. Now, because this cross-sectional area of the hydrometer is a circular something, we can express the cross-sectional area in terms of area of a circle. And the area of a circle is pi r squared times h. So let's equate mass of hydrometer is equal to density of liquid displaced times the volume of liquid displaced is being expressed as pi r squared h. Now, I said this is what we usually use to test students. Calculate when given the mass of the hydro, density of the liquid, calculate the height of immersion, meaning when the cross-sectional area is given times A. All that they are saying is that find H. Sometimes you can be asked to find the cross-sectional area of the hydrometer, A, or radius. So all that I'm saying is that when you understand this concept, okay, that is what will help you in solving questions under hydro, because it's basically this. Sometimes the liquid's relative density will be given. Okay, but what is relative density? Relative density RD is equal to density of density of substance, whatever substance it is, divided by density of equal volume of water. So numerically, whenever you are given RD of a substance is equal to the numerical value of its relative density. So, assuming this is given to me as 2.5, the relative density of a substance is 2.5. This value is equal to the density of the substance in gram per centimeter cube, because density of substance divided by density of equal volume of water. The density of equal volume of water is 1 gram per cm cube. So it means that the density of the substance would be 2.5 gram per cm cube. All that I'm saying is that if you are given RD of a substance in gram per cm cube, if you are given RD of a substance, it is equal to the density of the substance in gram per cm cube. Okay, so in case you are not given the density of the substance or liquid direct and they give you its relative density, you can pick the density from this. All right, any question? I'll look for questions on the hydrometer and then send it to you, okay, to try your hands on, so that as I cross-check whatever you've presented, we can use that to understand this concept taught. But all that you need is this explanation. All right. Okay. Can I clean the board? Because we are moving on to the hydrometer. Do I clean the board, class? Hey, today you are not talking. No. What's your secret? The hot air balloon. The hot air balloon is something that is used for exploration, tourism. I remember before COVID, or Cowbell Ghana, Promasodol Ghana Limited, launched it in Ghana, and people were taken on board for exploration. I learned a lot of celebrities, the movie, and then the music industry players, a lot of them were on board taking pictures. So it was so famous in Ghana. Okay, I'm sure some of you know about the hot air balloon. True or false? If you know about the hot air balloon, let me hear your voice.
Sir, I do.
Okay, so it is just like a balloon fabric. A balloon fabric, not the balloon we play with. A very large balloon fabric. When you go online, you can even get a video connected to something, a basket-like thing. It is usually tied to a container. And people can go on board, sit within the basket for tourism purposes. So these are people on board. Now let's look at the principle of operation of the hot air balloon. The principle of operation is that it works on the principle of flotation, and that is weight of objects must be equal to weight of fluid, weight of air. Here, our fluid is air, displaced. Or since weight of air displaced is also equal to upthrust, we can say that the weight of balloon is equal to the upthrust by the surrounding air, by the surrounding air. Now, when we talk about balloon, we are talking about the balloon fabric itself plus all the people on board. So the balloon, weight of balloon includes weight of balloon fabric plus weight of people on board plus the weight of the inert gas within the balloon. Let's look at how it works. The balloon, hot air balloon, is launched at windy areas. We don't launch it at just anywhere. It is often launched from areas which is so windy. The wind velocity is so high. Now, before it is launched, okay, they want the total weight of everything within the balloon, including the people on board, whatever they are in with, the gas, and then the balloon fabric, to be less than the upthrust supplied by the surrounding air. You know, we cannot change the upthrust because upthrust has to do with density of the surrounding air, volume of air displaced by the balloon. Okay, now don't forget, upthrust U is directly proportional to density, directly proportional to the volume of air or fluid displaced. And density of surrounding air, we cannot do anything about it because that is a constant value depending on natural factors. But the volume of air displaced can be changed. And that is, the larger the size of the balloon, the larger will be the volume of air displaced. So the hot air balloon is usually a large balloon fabric. The reason is that because for it to displace large volume of air, that is why it is made of, it is crafted in such a way that it is huge in volume. So we can always control this. If we can control this, then we can vary upthrust, rho Vg. As for gravity, that is also constant. Okay. Now, because U must be greater than the entire weight of the balloon, entire weight of the balloon, what they usually do is that the balloon is filled with inert gas, such as hydrogen, helium, or argon. Argon is usually the preferred inert gas. Inert gases are very, very light. Their density is so low. So the balloon is first filled with any of these inert gases, argon. So the inert gases, I'm talking of hydrogen, helium, and argon. And these are gases with very low densities. Their density very, very low. So the balloon fabric is first filled with inert, one of these inert gases. Then, apart from it being filled with the inert gas, it is also heated. So there is usually a source of fire within the balloon. There's also a source of fire placed within the balloon. Now, before they take off, the chamber has to be heated. The reason for the heating is that air becomes light when heated. Air becomes light when heated. That is why if you are in a room and the room feels so hot, okay, the obvious advice is that open the louvers and the windows, because when you open the windows, because warm air is always lighter, it can easily be displaced by cool air from outside. So cool air from outside blows the warm air, throws it away, okay? And so when air becomes heated, it is lighter. And so we are filling this with inert gas, which is naturally lighter. We are heating the chamber so that the lighter inert gas will be lighter the more. And the whole idea is that we want this to be the entire weight of the balloon to be less than the upthrust of the surrounding air. And if that condition is met, it can easily, the upthrust can easily buoy it up or push it up. Okay, so it is heated to a certain temperature. They've done their in-house calculation, so they know the volume of gas to fill this with. They know the time of heating and then the temperature, so that it will be lighter as they desire. So that is the reason for which they have air chamber and all that. Okay, so when it has been heated to that margin, I said it is always launched at windy areas, just as paragliding, parachuting, Kwahu. It is only done at Kwahu Ridge because the landscape there would enable that. Equally, hot air balloon is also launched at windy areas. So when they have done all this, the upthrust U becomes greater than the entire weight of the balloon. The entire weight of the balloon. Then a body always accelerates when there is a resultant force or a net force. So because U is greater than this, there will be a net force between the two, and there will be acceleration, vertical acceleration of the balloon. Please, if you have any question, ask before we continue. Any question? Any question here? All right. So when U is greater than the total weight of the balloon, then the balloon gradually moves up, 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 and accelerates vertically. Now, once it is accelerating vertically, then we expect that the hot air balloon goes on non-stopped because it is accelerating vertically. And so it will continue to go on and on and on. Yes, but it doesn't continue to go non-stopped. There is a time where the hot air balloon stops and then floats, move horizontally in the sky. Okay, we say it floats in the sky. When does it float in the sky? You see, air is such that the higher we go, the less dense air becomes. So the higher we go, the less dense air becomes. The higher we go, the less dense air becomes. Now, if that is the case, this is actually the reason why those mountaineers, those who climb mountain, okay, when they are climbing mountain, they need to go with their pack of oxygen container, because the higher we go, the less dense the air becomes. Meaning when you get to a certain altitude, you cannot have adequate oxygen to breathe, to sustain your life. So if you don't make that intervention, you go up there and you'll be bleeding from the nose. So to prevent that, when those who climb mountain Afadjato, Kilimanjaro, and Everest, when they are going, they go with oxygen, because as you go up, oxygen becomes less, and so breathing becomes difficult. So the higher we go, the less dense the air becomes. Meaning as you go, we go up, the density of air, which we are taking as approximately 1,000 grams per cm cube, reduces. If it is reducing, it means that as we go up, the upthrust which is pushing the balloon up is given by rho Vg. V is constant. V has to do with the volume of the balloon fabric. Okay, the larger the balloon fabric, the larger volume of air that will be displaced. Gravity is also constant. Yes, it is true. As we go up, gravity to some height decreases, but we usually cannot go within that height to reduce G. So we can say that gravity is constant so long as we stay within the Earth atmosphere. It is when we move beyond that gravity changes. So V is constant, G is also constant. But rho is changing because we are going up. I said the higher we go, the lesser the concentration of air becomes. So as we are going up, V would be decreasing. Okay. Now, if V is decreasing, then it means that upthrust as we go up will be decreasing. It will decrease, and get to a point where the entire weight of the balloon, is equal to upthrust, there will be a point, a height, where the upthrust will just be equal to the weight of the balloon fabric. Then, the moment this condition is obtained or achieved, the balloon ceases to go up and then floats, because there's a condition for flotation. Then the balloon will just be floating in air, moving horizontally. This is how the hot air balloon floats. Okay, so for it to take off, the upthrust U must be greater than the entire weight of the balloon, which includes the people on board, okay, the balloon fabric, and then the weight of the inert gas within. When U is greater, the balloon would accelerate vertically upward. Now, because of the fact that as we go up, the density of air decreases, upthrust will be reducing gradually. There will be a point where, because rho is decreasing, okay, U will just be equal to the entire weight of the balloon. At that point, the balloon ceases to go up vertically, but floats horizontally in the air. Okay. Now the question is, how do they come back? I want you to brainstorm and tell me, if they want to come back, one of the things they need to do. Just look at the conditions I explained. What they need to do. So when they are coming back, what do you think will be one of the possible things they would have to do for the balloon to begin to come down instead of floating in the air? Mamiya?
They will extinguish the fire in the hot air balloon.
The first thing is to extinguish the fire. Mamiya, why? And when they extinguish the fire, what do you think will happen? Caleb, please let Mamiya explain, then we continue. Mamiya, when the fire is extinguished, what do you think will happen?
The fire was applied in the first place because warm air is lighter. So if they extinguish the fire, then it means that the air inside the balloon will become very dense. So then it will become denser than the air around it, then to start to calm down because it will be heavier.
Thank you. Thank you for the explanation. All right. So one obvious thing is that the fire must be extinguished. So they put off the fire. Caleb, your hand was up.
So please, I think that first they would let some of the gas out, so that as the gas is coming out, the density of the air in the balloon would increase, because now the mass has increased and now the air is occupying less volume. So it would be descending densely. And while they are doing this, they would make sure they are reducing the intensity of the flames that they are burning.
Okay. What they actually do is, in fact, extinguishing the fire. Once the fire is extinguished, then it will not be warmed again to be lighter. Now it will be dense. Okay. And once it's denser than the surrounding air, then they can achieve a situation where the weight of the balloon is greater than the weight of the surrounding air, or the density. But apart from extinguishing the fire, it is also piloted. If it is not piloted, there is a chances of landing in a tree, along a tall tree, or landing on somebody's building. Okay, so it is piloted. But the first thing they do is to off the fire within. Then, okay, gradually piloted to wherever they want to, get to. All right. So when they want to come back, the whole thing is that they want to reverse the trend, make the whole component lighter, so that this time they can accelerate downwards instead. All right. So this is the principle of operation of the hot air balloon. You can be asked to explain why the fume chamber, why do they fill it with inert gas? When they fill it with so and so gas, whose density is greater than this? What do you think will happen? And all that. Is that okay? And how you must understand that when it is taken off, the density of the surrounding air, okay, the upthrust must be greater than the entire weight of the balloon. And when it gets to that, when the reason for which it cannot go up, accelerate vertically upward throughout, okay, you must understand those things. And then use the principle of flotation to do these calculations about the hot air balloon. Mamiya?
Please, I don't still understand why the upthrust needs to be greater than the weight of the balloon.
Mamiya, before you can lift your sister up, if your sister is weightier than you, can you be able to carry her up?
No, please.
If the weight of your sister is greater than yourself, or the force you can apply, you cannot, okay, carry her. Meaning that for you to be able to move her up, you must have strength greater than, or apply force greater than the weight of your sister. The reason for which the upthrust must be greater than the surrounding, the upthrust of the surrounding air must be greater than the entire weight of the balloon so that it can lift it up. Are you okay?
Yes, please.
All right. Please, is there any other question? That is why I said that now as the balloon moves up, because the density of air as we move up decreases, upthrust will be reducing. Upthrust will be reducing and will come to a point where the weight of the balloon is just equal to the upthrust. Then at that point, the balloon wouldn't go up again, but would float within the air because we have obtained a condition for flotation. All right. I'll send questions so we can be trying, okay? As you go through the questions, then we correct mistakes and all that. Please, if you have any question, ask. If you don't have any question, we are moving on to another area. Moment, Jojo and Co. Please, Disco guys, and I ask you to send me work sets given to you so that we'll incorporate it or factor it into our program. Okay. I'm going to start with one of the topics given to GH students to try. I think you are to read on moments. You are also to look at geometric optics, what you call as lights. Light is a broad topic. As for moment of a force, we can do it within, few days. So if you have reading assignment given to you, please forward it to me so that I'll add it to my program. moment. Not just moment, but moment of a force. Let me draw your attention to areas where we apply moment of a force. Whenever you are opening your door, okay, there's a door handle which has to be turned for the knob or for the door lock to actually unlock, to aid you to enter into the room. Apart from the door handle, you also, the whole door frame, okay, connected to a wooden frame or connected to the hinge, you exert a force on the door frame or the door lock, the handle, and then it turns through an angle, an application of moment. When we were kids, we were playing on this seesaw, but our seesaw was the kind that has a long bar and then pivoted at a point. Now one person sits here at one side, another sits at the other side, and then we will just be seesawing, an application of moment. Whenever you are using a screwdriver, you put it in position, pivot it, and then apply a force in that angular or directional manner to unscrew. Moment. Opening soft drink. The opener is hinged at one end and then force is applied at the other end. Moment. Removing nail from wood using the screwdriver. Okay, moment. Can you discuss some applications you have actually noticed with us apart from those mentioned? Can you also identify any application of this sort and share it with the class? Any application similar to the ones I've just indicated? Anybody? Or I've mentioned everything? Jojo, Mamiya, Udrick, Della, Eva, Frida, Gabby, Henry, Infinite Notes. All right. Okay, so these are some applications of moments mentioned. Now, the question is, what is the moment of a force? If you've read around something like that, can you share it with us? What is the moment of a force? Anybody? Anybody? Udrick.
Sir, please, it is the force times the perpendicular distance of an object.
Udrick, you are right, but I won't take this to be definition of moment. I'll take this to be how to calculate moment. So,
yes, sir.
What is the moment of a force? Anybody? Udrick has given us something. So If you have any, share it with us. I want to drop the attendance on the platform, so I'm waiting for you.
Recording in progress.
Yes. Oh, Mommy, yeah. Jojo. Joel. Julian, Cadmiel. What is the moment of a force? Okay. I'm coming in. Let me take a shot of. I want to drop the attendance on the platform. All right. So the moment of a force is defined as the turning effect produced by a force. The turning effect produced by a force. Come in. Okay. So it is the turning effect produced by moment of a force by the turning effect produced by a force. Okay. The turning effect produced by a force. So look at the examples indicated. Opening the door, you apply a force. Okay, through a load, a distance around a pivot. So your door hinge, okay, your door hinge is such that you have to hold the outer end of the door handle, which is often like this. Okay, you hold it, it is hinged at a point. Okay, so you hold this end, then you turn for the door to open. Now the point is that imagine opening your door, and then instead of holding the outer end, you hold it this way at a point close to the pivot. Turning becomes so difficult. If you are using the crowbar, okay, and then you hinge it to a nail and you want to turn, you must always do so holding the outer end and then applying the force. If you hold a point close to the nail, turning becomes difficult. Is that okay? So the moment of a force is actually the turning effect produced by a force, and it is determined by the product of the force. Moment is equal to, how to calculate it? Is equal to the product of the force times the perpendicular, the product of the force and the perpendicular distance. Perpendicular distance from the axis of rotation or the pivots. Okay, so look at this illustration. Mamiya is here applying force downwards. F. If we want to calculate the turning effect produced by Mamiya, It is the force applied by Mamiya, and then this distance from the pivot. This distance. But the distance must always be perpendicular to the force. The distance D around the pivot must be perpendicular to the pivot. So the moment is equal to the force times the perpendicular distance. So what we mean here is that for moment, it isn't just any distance, but the distance must be perpendicular to the force. Okay, so we are always looking for a distance which is perpendicular to the force, or a force which is perpendicular to the distance to calculate moment. And if this peculiar relationship is not there, then moment would have just be the same as work done, because work done is also force times distance. For work done, we are looking at just distance, product of the two. But for moment, we are careful. We are always looking for the perpendicular distance to the force, or perpendicular force to the distance. So this is how to measure moment. Let's look at the SI unit. What do you think if moment is force times distance? What do you think will be the SI unit for determining moment, or for moment? Yes. Jojo.
It's a Newton meter.
So it can be Newton meter, force Newton, perpendicular distance meter. Other units, can somebody help me with the derived unit of moment? The derived unit. Yes, the derived unit. Oh, Udrick. Udrick, go ahead. Oh, Edric or Udrick.
Sir, please, kgm.
Oh, say it well. Kilogram.
Kilogram per meter.
Open your eyes well.
Sir, please, kilogram meter. Yes.
What is the derived unit of force?
Kilograms per meter square.
Kilogram meter per second squared. Kilogram meter per second squared times m. So kilogram meter squared per second squared. Kilogram meter squared per second squared, or writing it in this manner. Okay, so this becomes the derived units. Now, so calculation of moment, we are saying that it is the force, product of the force and then the perpendicular distance. So let's look at two instances. We have, this is the axis of rotation, what we call as pivots. In this particular situation, we have F1 acting at a distance of x centimeter from the pivot. And the relationship is that this is perpendicular. Now we also have this force F2 acting at an angle of, this is 120 degrees. At a distance of y from the pivot. And the instruction is that determine the net torque or turning effect instead of torque, because I'll talk about this. Determine the net turning effect. So the turning effect produced by this force F1 or the moment, instead of using turning effect, the moment by F1. Moment is the product of the force and the perpendicular distance to the point or to the axis of rotation. So this would be F1 by X. That's the turning effect produced by F1. Then moment by F2. We are saying that moment is the product of the force and the perpendicular distance. So if the force isn't perpendicular to the distance, or the distance isn't perpendicular to the force, we can easily calculate moment. So we need to resolve this force and get a component of this force which will be perpendicular to the distance before we can find moment. So how do we get a component of this force F2 which will be perpendicular to the distance y? We resolve using our vectors, using the idea of vectors. Now, if this is 120, the remaining angle here becomes 60. So 60 degrees complements 120. So let's resolve force F2 with the angle 60. When we resolve this, the vertical component of the force F2, becomes, yes, help me determine the vertical component of this force to the angle 60. Anybody? The vertical component of this force F2 with the angle 60. Oh, who is helping me out? Okay, Audrey.
Sir, please, negative F sine 60.
Why negative F? Because it's down.
Yes, please.
Oh, we are not looking at the direction, okay? And
yes, sir.
By this, it doesn't emphatically means it's down because we are looking at component of forces. So this is F sine 60 degrees. Then the horizontal component What's the horizontal component? Mamiya, what's the horizontal component of this force? Oh, let's be quick with our view.
Breathe.
So this is
F2.
F2 cos 60 degrees. Now, the vertical component, the horizontal component are perpendicular by equal vectors. This vertical component can equally be here because vectors are equal when they have the same magnitude and direction, irrespective of wherever they are. So this F2 sine 60 can equally be here. So long as they have the same magnitude, direction, and are perpendicular, parallel to each other. Meaning that we've managed to get a component of this force which is perpendicular to this distance. And so we can calculate for the moment. Therefore, moment of the force F2 would be equal to of course, moment is force, the product of the force and the perpendicular distance. Okay, so the force which is now perpendicular to this distance is F2 sine 60 times the distance y. So until you have determined the component which is perpendicular to the force, you cannot just calculate it if it is not directly perpendicular. Meaning, if I'm given any angle theta, we want to create a general formula. So instead of 60, let me use an angle theta. This force makes an angle theta with the bar. By resolving, if this is theta, then this will also be 180 minus theta. So that this component becomes F2 sine times the sine of 180 minus theta. By equal vectors, this component can be written here. F2 times the sine of 180 minus theta. Therefore, the turning effect produced by this, the moment by F2 becomes the force, which is F2 sine 180 minus theta times y. Now let's expand 180 sine 180 minus theta. If you have a compound angle A minus B, the expansion of this is equal to sine A cos B minus cos A sine B. Sine A cos B minus cos A sine B. So let's apply this in expanding whatever we have here. Sine 180 minus theta will be sine of 180 times cos of theta minus cos of 180 times sine of theta. Now, what is sine 180? What is sine 180? Check on your calculator. Give me the value of sine 180. I guess it's 0. Confirm.
Yes, please.
So this is, if sine 180 is 0, then the whole of this part goes to 0. Cos 180 is negative 1. So negative 1 sine of theta, which is equal to sine theta. What we have done is that sine 180 minus theta is equal to sine theta. So it means if you give me sine 120, it is equal to sine 60. Sine 30 is equal to sine 150. Sine 20 is equal to sine 160, and so on and so forth. Meaning that this whole thing, the moment can simply be f2 sine 60, sine theta times y. So when you are given any distance d acting at an angle theta, the product of the moment is fd sine theta. That is basically what it means. Where F is the force, D is the distance, and sine of theta is the sine of the angle. So when a force acts at any angle, okay, to a pivot, this is how to calculate for the moment. Let's solve example using real numbers. So I'm told that F2 acts at maybe 5 centimeter. This is 5 centimeter around the pivot. The force of 100 Newton acts at an angle of 120 degrees from the pivot. Calculate the turning effect produced by this force. I want you to try using the idea illustrated. Calculate the turning effect produced by this force. Try first before I come in. We are only looking at, there's a pivot here. A force of 100 Newton acts at a distance of 5 centimeters from the pivot at an angle 120. Calculate the turning effect produced by this force. Are you done? Eva, are you there? Hello, Eva. Oh, Eva is gone. Angel, are you done? Della? Frida? Jojo? Hello, are you done? Hey, no one is talking.
Please, I have 433 Newton meter.
433 Newton meter. Okay, any seconder? Anyone getting the same or different value? Leonard, Odrick, Caleb.
Sir, please, I had the same thing.
Okay, all right, then let's go through it. So when we resolve this part can be equal to 100 sine 60. And this is the part perpendicular to the pivot. So the turning effect produced by this or moment is 100 sine of 60 times the perpendicular distance 5 centimeters. What is sine 60? Sine 60 is root 3 on 2. So 100 times root 3 on 2 times 5. This is 50 root of 3 times 5. So 250 root 3 Newton centimeter, or 250 root 3. 250 times root of 3 is equal to 433. 433 Newton centimeter. Or I want to change the centimeter to meter. Centimeter to meter is times 10 to the power -2. Or 433 divided by 100 changes this from centimeter to meter. So 124.33 Newton meter. So these are the two possible answers. Okay, either 433 Newton centimeter or 4.33 Newton meter. Please, is that okay?
Yes, sir.
Another question. So we have a long bar pivoted at one point. There are a number of forces acting in different manner. This is 50 Newton. Let me make this 50 kilogram. From this point to this point, we have, this is 3 centimeter. Then we have another force. This one is here. This is 50. This is 20 kilogram acting at an angle of 60 degree. It's just a modification of 60. Then we have another one acting here. Another force acting here. This is 50 kg. The question is that calculate for the net torque. For the net turning effect. Yes. Start work. We have to calculate for the net turning effect. This time we have a number of forces acting on the bar, 3 of them. 3 of them. Let me include another one. This is 10 kilogram. It acts on a pivot. What will be the net? The net. Net is the difference. The scenario I've created is similar to having a bar, 2 people sitting here in different angles. One sitting at the end, 3 centimeters from the pivot. Another person just sitting on the pivot. Who turns the other? And what will be the direction of the turning? This is what the net torque means. Which one wins? It's like seesaw. But this time it's on a pivot, on a bar. They are not pulling, but weights are being exerted. Who turns the other, and what will be the direction of turning? Will it act in the direction of these ones or these ones? So 3 minutes, just think through it for 3 minutes. Let's see what you can do. Then we discuss.
Sir, please, the lighting, I can't see the direction of the last force. The 50 kilograms, I can't see its distance.
It's 3.
3.
Which one?
Thank you.
Is it this one?
50 kilograms. No, sir. Please,
No.
the last one.
It's
The one
3.
at the last. Okay, thank you, sir.
Welcome. I've also dropped the question on the platform. Discuss it. Okay, so what is the way forward? The way forward is this. Determine the turning effect produced by each of the weights or masses. So to determine the turning effect produced by this is 20 times sine 60. Sine 60 times 5. Then this one too. This is 50 times 5. This is equal to sin 60, 10 root 3 times 5, which is 50. 50 root 3 kilogram centimeter plus 250 kilogram per kilogram centimeter. Kilogram centimeter. This is whatever prevails at the left-hand side of the pivot. This is the pivot P. So whatever prevails at the left-hand side of the pivot, this is it. Let's look at the right-hand side. When there is a force or mass acting just at the pivot, the turning effect produced is 0. Why 0? 0 because we are defining moment as force or mass times perpendicular distance. So this is the mass. Where is the perpendicular distance? Is 0. So whenever a force or mass just acts at the pivot, the turning effect produced is 0 because there's no perpendicular distance. Come to look at this one. This will be 50 times 3. 150 kilogram centimeter. So when you compare the two, the turning effect produced by this side, by this one, okay, is far, far greater than the turning effect produced by the right-hand side. So the net turning effect will be the difference between them. Is equal to 50 root 3. Let's express 50 root 3 in decimal so we can add the other one. Plus 250. 33, approximately 337. Minus 150. So approximately 187 kilogram per kilogram centimeter is the net turning effect. So this is what we mean by net turning effect. You calculate for my earpiece is gone. All right. So with the net turning effect, we calculate for the total turning effect or moment at one side. Calculate for the total turning effect at the other side, and then find the difference. So it means these people here will turn this one. So if these are people, those number here, okay, will turn these ones up here, or the bar turns in the direction of this one, downward. Please, is that okay? Somebody may be wondering why I did not express the weight as the masses as a force. You can equally do that. Don't forget, force or weight and mass relate. The only difference between them is gravity. the reason for which weight is mg. So you can always switch from weights and masses to weight or forces by this. Okay, so you can equally express each one, okay, as a force or weight and use it to calculate that. In that sense, then it will become Newton centimeter when you decide to multiply them by gravity and all that. Please, is that okay? If you have any question, ask. Yes? Udrich.
Sir, please, why is that the 20 sin 60? You didn't make it 20
Udrich, go ahead with your question.
Sir, please, why is it that the
Oh,
20
I'm listening.
20 kilograms? Sir, please, the 20 kilograms, it was 20 sin 60
Udrich.
rather than. Hey, sir,
I'm
never
not
mind.
hearing what
I've
you're
answered.
saying.
Sir, please, okay, I've answered my own question.
Okay. Maybe it's a network challenge, so you can send your question to me on WhatsApp, okay, so as to answer. All right. So please, is there any question? All right. If there is no question, then I'll send a couple of assignments to you to try on whatever we've done for the day. We have about 5 minutes to end the show. So we'll end here and then I'll upload your assignment to try on hot air balloon, hydrometer, and then these ones. Okay. I think this time, I think you may have about 2 different work sets, simple ones to try. So when it comes, please, I'm urging each one of you to be involved whenever there's assignments. Okay, just do your part. Just do your part. Let me know what you think. Correct. And as I critique on your works, in fact, you get better. So I'm urging each one of you to be involved in assignments. I only had, okay, I think the last assignment I gave, I only had less than 30 of you submitting your work. Let me check. Okay, I only 31 of you. Meanwhile, we are more than 40 on this platform. So please, whenever you are giving work sets, try as much as possible to do your part. Even if you don't understand, please let me know to see how best I can help you. Okay, that is better than deciding not to, be involved, okay, in the whole thing. All right, so this is why I draw the curtains on today's meeting. As usual, I'll upload the video so that you can always review it for correction and all that. Okay, take care of yourselves and have a wonderful day. Bye-bye.
Bye.
Bye.
Bye.